Hi, this is analysis of algorithms. We're doing chapter 8, which is called sorting in linear time. Okay, so last time we did chapter 6 and chapter 7. We did two different sorting things, and we want to sum up all about sorting and get to some interesting cases. Okay, so let's just recap what we saw. We did basically the first day of the first chapter, we did the insertion sort and the merge sort. And then chapter 6 was heap sort and chapter 7 was quick sort. And we want to look at them all in the worst case, the average case, and the best case. The insertion sort was n squared, n. Okay, merge sort was n log n, n log n, n log n. Heap sort was n log n, n log n, n log n. Okay, for both of these, we never care what the state of the data is. It's always n log n. You're always building the heap. You're always merging the data. It doesn't matter whether it's good data or bad data. As opposed to that, for quick sort, we said in the average case it's n log n, in the best case it's n log n, but in the worst case, which happens very, very, very rarely, it's n squared. Okay, so that's what we saw. And now comes the obvious question. Can we do better? Okay, can we find an algorithm that does better than n log n sorting? Okay, and so we want to start off doing this. We want to think about a new way of doing sorting. Okay, we want to think of a new way of thinking about how sorting is done. Okay, and the idea is as follows. Let's say you have 3 cards. Hold on. Let's say you have 3 cards, A, B, C. They correspond to numbers. Okay? I want to talk about an algorithm that's going to sort them. Now just think about it. What's the possible outcomes of your algorithm? Well, it could be A is first, B is second, C is... So that's one possibility. 2 possibilities. A third possibility is B is first and then AC. Fourth possibility, CA. Or fifth possibility, C is first, then A and B, or then B and A. So altogether there are 6 possibilities. So I'd like to describe, you're given 3 numbers, you don't know what the order is. I'd like to describe a way of writing the order. So one of the ways you could do it is as follows. It's called a decision tree. Okay, and the way it goes is as follows. You have 3 cards. You can ask the following question, A less than B. Okay? And there's 2 answers to that, yes and no. Now, if you know that A is less than B, okay, now you can ask another question about C. So you can ask the following question. Question, is B less than C? If B is less than C, then this is an ascending order, then you know that the final results is, first is A, then this is B, and then this C. Okay, but let's say you know A is less than B, but the answer here was no. B is not less than C. So now you have to ask another question. Question, is it like this, CAB, or is it ABC? You know A is less than B, that's why you're here. Now you asked, is B less than C? You got a no answer. So now you have to worry, is it here or is it here? So you might as well ask this. Question, is A less than C? Okay? If A is less than C, then that's your answer. And so if you have a yes here, then your answer is A, C, B. Okay? If the answer is no, A is not less than C, then your answer is C, A, B. Okay? That's great. What happens if A is not less than B? So your answer is no. So I ask, is A less than B? And the answer is no, so we know it's like that. Okay, good. Now what's a good question to ask? Is A less than C? Is A less than C? If A is less than C, then you know. If the answer is yes, then you know the answer is B, A, C. If the answer is no, okay, so let's go through this. A less than B, no, B is less than A. Okay, A less than C? No. Okay, so then what do you know? If A is less than C, then it's BAC. If not, you have B C A. 1, 2, 3, 4. No. Well, then you have to ask. Question: is B less than C? And if the answer is yes, then you have, if B is less than C, then you have what? B C A. That's a yes. If no, then what do you have? C B A. Okay? Okay, so this is the way to think of an algorithm as a tree. But let's go through some features of this tree. 1, how many leaves does the tree have? 1, 2, 3, 4, 5, 6. There are 6. Why? Because there are 6 possible outputs for 3 cards. If you don't know 3 numbers, there are 6 possible outputs, because 3 times, there's 3 possibilities for the first number, 2 possibilities for the second, 1 for the third. 3 factorial. 3 factorial is 6. Okay? So there are 6 possible outcomes. 1, 2, 3, 4. Question: how much work does this algorithm do? And the answer is the maximum number of questions to go from the root to a leaf is the number of, that's the number of comparisons. That's how much work is done. 1, 2, here you had only 2 questions. 1, 2, 3. Okay, then you get to an output. 1, 2, you get to an output. 1, 2, 3. So the maximum number height of the tree is basically h, the height of the tree is basically the number of questions you're asking. Okay, great. So this is the way to think about algorithms, and there's specific types of algorithms. Okay, and now I just want to say we can also ask what happens if I had 4 nodes, 4 things. Well, then I have to ask another question. For example, is C less than D? Yes or no? Okay. Okay. So if I had 4 cards, 4 unknown numbers, question: how many leaves would I have then? Well, I'd have 4 possibilities for the first position, 3 possibilities for the second position, 2 possibilities for the third, and 1 possibility for the fifth. That's 24. So this is 4 factorial, which is equal to 24 leaves, if I had 4 cards. In general, if I have n cards, I have n factorial leaves. Okay, which is the amount of possible outputs you would have for a sorting algorithm. If you're sorting n cards, n things, you can have n factorial possible outputs. Question: how many questions do you have to ask in order to get in the worst case, how many questions do you have to ask to get to those 4 factorial possibilities? Okay. Now, in the handout that I gave, I show you different algorithms and their decision trees for the insertion sort. Okay, different algorithms and their insertions, and the decision trees for those algorithms. Here's the insertion sort. Okay, and it shows you how the insertion sort works. Okay, basically you assume A is in the right place, and you're trying to put B into the right place, and you do it like that. In contrast, the other algorithm I show in here is the decision tree for the selection sort. I don't know if I told you about selection sort, but it's something you can easily tell. Notice here, for the insertion sort, sometimes you ask 3 questions, sometimes you ask 2 questions. For the selection sort, you're always asking 3 questions. So this is worse. You're doing more work. You're asking more questions for that. Okay? I just want to show you, what would happen for the bubble sort. Hold on. Well, we'll do it with a pen. Okay, here's how bubble sort works. I'm sure you've seen bubble sort, although you're not supposed to use it, but basically okay, how does bubble sort work? Well, you compare these two, and you swap them if this belongs that way. And then you compare these two, and then you compare these two, and then you compare these two, and then you back up and compare and compare and compare. Keeping on backing up and back until you do the entire thing without making any changes. The idea of the bubble sort, and if you've never seen the bubble sort, you're not going to learn it now, but you should see it. The idea of the bubble sort is that the larger number bubbles to the top. Okay, but the point is, you're always asking questions that you might already know. In other words, even if you go through it, you're only going to stop when you don't make any changes, which means that all these numbers you know is in the right place. But you already asked those questions, so in some sense the bubble sort has a lot of redundant questions for you. Okay, the decision tree for the bubble sort looks something like this. Notice there's a lot of questions that you get yes answers, and it keeps on going. It's a long time. The bubble sort is not a good sort because the decision tree is very long. Okay, good. So the idea is as follows. For every algorithm, sorting algorithm, there is a decision tree. Okay. For n cards, there are n factorial leaves. The height of the decision tree what's the height of the tree? It's the longest path from a root to a leaf. That's the height of a tree. So the height of the decision tree is the work that is done. Okay, good. So every sorting algorithm is a decision tree. These decision trees have n factorial leaves. The height of the decision tree is the work that is done. Good. Now we ask the following question. We went through 4 different sorting algorithms. Question, is there some better algorithm? Okay, is there a better algorithm than n log n? Can we do better? Okay, and the answer is as follows. Ready? Even if you had some magic algorithm that never asked a redundant question, that never asked a question, that only asked the exact questions to get the perfect output, still you would have n factorial leaves on a binary tree. Okay. Why is the tree binary? Because you're asking questions. Is x less than y? Those questions have yes, no answers. So it has 2 children. Okay. By the way, we can ask other types of questions. We can ask questions like this. X, y, is they less than? Are they equal to? Are they more than? Okay. And then we'd have a trinary tree. But we're not dealing with that. We're dealing with binary trees. We're asking if one number is less than another, and we're getting that. Okay, so you have n factorial leaves on a binary tree. And now I'm asking the following question. What is the minimum height of a binary tree with n factorial leaves? Okay. Okay, because that's the type of tree we're going to get. We're going to get a tree with n factorial leaves because that's the possible outputs of a sorting algorithm, n factorial leaves. Okay, and we want to know what's the shortest because the shortest corresponds to the best possible algorithm. Okay, and so you have something like this. The book does this, and we're not responsible for it, but the book does it. N factorial is less than or equal to 2 to the h. Okay, that's how many leaves you need, and the height of a tree is going to be, you're going to have 2 to the h leaves in the height of a tree. So now we solve for h. Okay, and now there's a little, you do log base 2 of both sides. Log base 2 of 2 to the h. Solving for h, so you get h is less than or equal to log 2 of n factorial. Okay, okay, and that turns out to be n log n. H is less than n log n. I'm sorry, n log n is less than h, which means you're not going to get a height of a tree smaller than n log n. Okay? You're not going to get the height of the tree smaller than n log n. Let's review. Every algorithm, there's a tree, a decision tree, a binary tree. Each one of these trees has n factorial leaves because that's the possible outputs you get. Now we ask, how much work is done by these trees? The height of the tree is the amount of work done. Okay? Well, it turns out if you're going to have n factorial possible leaves, there's no way to get a tree that's going to be smaller than n log n. Conclusion, you can't get better than n log n. So we saw all these things. Some of them work n squared, but in the worst case scenario, you're not going to get better than n log n. That's the content of section 8.1. A little bit in math we skipped over here, but that's fine. You can try to read it on your own in the book, but it's very nice. That's the content. So no matter how good of a programmer you are, you're not going to get better than n log n. Okay, great. Okay. What's the title of this chapter? Sorting in linear time. Linear, that's n. That's better than n log n. Okay, so I'd like to show you how they do that. So again, we spent the first 20 minutes proving that you're not going to get it better than n log n, and now I'm showing you we're going to do something better than it. So it's the sorting algorithm. Let's do section 8.2. Called the counting algorithm. Okay, and what I'd like to do is show you how it works, and then we'll write the algorithm here. Okay, so it goes as follows. You start off with a matrix A, and the matrix is going to have 12 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it's going to have, these are the numbers, 5, 3, 1, 5, 6, 2, 4, 1, 5, 2, 4, 1. Okay? Okay, I'd like to sort these numbers. Okay, now particularly, these are easy numbers to sort. Notice I'm only going from 1 to 6. Okay, so what I do is I make a counting array, and since I only have numbers from 1 to 6, I only keep track of 1, 2, 3, 4, 5, 6. Okay, and now I'm going to count how many each of these numbers I have. So here's the way I do it. I go through the array and I add up what I have. So let's go. Ready? Start off, set all the counters to 0. So you see them as 0. Okay, there's nothing there. And then look, I have a 5. I have a 3. I have a 1. I have a 5, I have a 6, I have a 2, I have a 4, I have a 1, I have a 5, I have a 2, I have a 4, I have a 1. Okay, let's count up what we have. We have a 3 here, 2 here. It's not coming out good. Okay, well, we can do it. 3, 2. I have a 1 here. I have a 2 here. Not good, not good. I have a 2 here. Okay, 3 here, and a 1 here. Okay, so I have 3 1s, 2 2s, 1 3, 2 4s, 3 5s, and 1 6. Let's just make sure that adds up to 12, because that's how many numbers. 3 plus 2 is 5, plus 1 is 6, plus 2 is 8, plus 3 is 11, plus 1 is 12. Okay, now, I'll do this in red, doesn't matter. I'm going to take C and I'm going to change it now. And you'll see why in a second. Okay, I'm going to take 3 over there. Okay, next I'm going to do 3 plus 2 is 5. I'm going to do it the other way. 1 plus 5 is 6. 2 plus 6 is 8. 3 plus 8 is 11. 1 plus 11 is 12. Okay. Okay. What did I just do? Listen to what I'm saying now. From 1 to 3 is going to be a 1 in it. Then from 4 to 5 is going to be a 2 in it. From 6 to 6 is going to be a 3. Then the next 2, from 7 to 8, is going to be a 4. Then from 9 to 11 is going to be a 5. And then from 12 to 6, from 12 to 12 is going to be a 6. So what these numbers correspond to is the last number that such a thing shows up. Okay? Okay. Okay. Now, I'd like to write the algorithm, and then we're going to follow the algorithm. Okay? Actually, we're going to write the slightly different. Okay, hold on. Okay, this is the algorithm that's going to do it. It's going to put this in order. It's on page 195 of the book. Okay, counting sort. But I gave a different answer. I gave a different thing here. My answer is wrong, but I'd like to go through why. So you can copy the black, leave the red alone, because I'm going to erase the red when we see what's wrong. Okay? So let's go through the way it works, and we're going to follow what I do, and then I'm going to tell you what's the problem with my method, and then we're going to do it the way the book does it. Okay? So let's go through it. Counting sort. A, that's the input that you get. B, that's going to be the output. We're going to create another array called B, okay, and it's going to have 12 things, which is going to get A but sorted, okay, and K is the number of different possible output elements that you could have in your array. If you notice here, we only have 6 things. It can be 1, 2, 3, 4, 5, or 6. Okay, K is usually a small number, and this is the way the counting sort works. We'll talk about when K is a large number in a minute. Okay, so the first thing you do is you set your counters to 0. You set your counters to 0. So that's when I started here. I set my counters to 0. So for I is equal to 0 to K, you set a 0 array counter over there. You'll see why. For J is equal to from 1 to A length. Okay, I goes through these things. J goes through all of these things. Okay, and you do as follows. Look at J. So you're going to start at 1 till 12. look at J, look at the element in J, 5, okay, and then look at the counter of the element in J, so we're looking for the counter of 5, and increment that counter, so we put a 1 over there. Then do it for 2. The element of 2 is A of 2 is 3. Look at the counter of 3 is over here, and we put a 1 over there. We increment the counter. Then look at 4. The element at 4 is 5. We look at the counter at 5, and we increment, etc., etc. And we keep on doing that. Okay, so that goes through this thing. Let's just go through counting. This is K operations. Okay. This is N operations. Okay. And now this change, I changed it. I'm not looking just how many elements, I want to know where the last place is. So look what I do. C of I is equal to C of I plus C of I minus 1. So watch, we start at 0, you get a 3. Then this guy is going to look at 2 plus the previous guy. 2 plus 3 is 5. 1 plus 5 is 6. 2 plus 6 is 8. 3 plus 8 is 11. 1 plus 11 is 12. So that's exactly what this does. By the way, how much work is done? This K thing's done here. I hate these stupid things. Okay. Okay, now for the thing. So here's the way I would do it, and again, this is in red. It's wrong, but I'll show you why it's wrong, and that's the more interesting question. Okay, so let's put down, we have 12 things here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here's the way I would do it. For I is equal to 1 to k, so go through the n counters and look what you do. For j is equal to, what's the previous end counter, plus 1, to this one, okay? And place b, that's b, the jth element should equal to I. Okay, so you go through this and you do it. So let's go through it. Okay, from 0 till 3, so 0 plus 1 is 0 plus 1 is 1. So look what we're going to do. We're going to take from 1 to 3, we're going to put a 1 there. 1, 1, 1. Then from 3 plus 1 till 5, so from 4 to 5, we're going to put a 2. 2, 2. Then from 5 plus 1, which is 6, till 6, we're going to put a 3. We get a 3. From 6 plus 1 is 7 till 8, we're going to put a 4, so we get 4, 4. Okay. From 8 plus 1, which is 9, till 11, we're going to put a 5, 5, 5, 5. And finally, from 11 plus 1 is 12, we're going to put, till 12, we're going to put a 6. Okay, that is this sorted. Okay. It works. The only problem is, this is called, I'm going to write the problem in red because we're going to get rid of it. Okay, this is a problem, and the problem is, it's not a stable sort. Not a stable sort. Okay, and I'm going to explain to you what a stable sort is in a second. Okay, so let me tell you what a stable sort is. You have an inbox. Your mail comes in an inbox. The inbox is sorted by date arriving. Now you're looking for something. Okay, you're looking for an email from Mr. Miller. So you change the sort. In other words, now your emails are sorted by date of arrival. You change the sort to be sorted by the sender. Okay. Now, question: how does the new? You have all your emails sent by Mr. Miller. How is that sorted within that? And the answer is, it's sorted by sent time. Okay, in other words, you're going to get your later emails from Mr. Miller after your earlier emails from Mr. Miller. Okay, that's called a stable sort. In other words, if you have one thing over here and one thing over here, and this goes before this, then if you sort it, this will go before that. Okay, let me give you an example here. I have 1, 5, 2, 5s, 3, 5s. X, I'm going to call this 5x, 5y, and 5z. Well, I would like that when I get my 5s, it satisfies this same thing. This should be 5x, this should be 5y, this should be 5z. Okay? I have 3 a's here. I'm going to call this 3 1s here. 1a, 1b, and 1c. I'd like this to be 1a, 1b, and 1c. Okay? The way I did it, it didn't really work. Okay? Trust me on this. I'm going to give you an example of where you have this in 2 minutes. So this bottom part doesn't work because it's not stable. It doesn't have earlier sorted things come to sorted things. Okay? What it has is sorted things going to unsorted thing. That's not stable, and that's not good. Okay, and trust me, I'm going to explain to you why we need this in 1 minute. So let's cross out what I did because it was stupid, and let's do what the counting sort tells you to do, and that's as follows. Okay, I'm going to do it in green because green works at the moment. And it goes as follows. 4j equals a dot length to 1, b of c of a of j equals a of j, and then we do c of a of j. That's your counter. Decrement your counter. Okay? And now I'd like to show you how this works with this new way of doing things. Okay? We have the same counters before. We have the original, then we count it, then we adjust the counters. Again, what are these numbers? They are the end points of where your numbers go. Okay? Good. Okay, now we do it. From j is equal to length to 1. Just like this is dealing with endpoints, we're going to deal with endpoints over here also. Okay, let's go through it. We're going to start from 12 down to 1. From 12 down to 1. Okay, I'm sorry, think of it this way. We're going to start from 12 down to 1. We're going to put it like that. Okay, let's go through it. Start at 12. A of 12 is 1. The counter of 1 is 3. B of 3 is equal to A of j. So they're going to put a 1 over here. By the way, which 1 are we putting? There are a few 1s here. There's 1a, there's 1b, there's 1c. I'm going to put 1c here. Okay, now that we did that, next thing, 12. A of 12 is 1. The counter decremented. The counter was 3, but you know what? We took this, and we did this, so let's decrement it and make that a 2. Okay, good. Let's go on. Next thing, 11. Okay, let's do this. 11, j is 11, a of j is 4. The counter at a of j is 2. I'm sorry, is 8. Let's do that again. J is 11. The contents of A of 11 is 4. The counter of the fourth element is in position 8. Okay, that's the final thing. So B of 8 is equal to 4. Okay, now decrement that counter. It was 8. We're going to make it 7. Okay, good. Next, Now we're doing 10. J is 10. We're going down. The counter was 2. I'm sorry, the contents was 2. The final counter for 2 is in position 5. So we're going to put a 2 here, and we're going to decrement the counter to 4. Okay, good. Next. Okay, next. Ooh, whoa, that's not good. Okay, next. 8, so we're up to 9. 5, okay. That's the 11th position, so we're going to put the 5 there. Which 5? 5Z. Okay, we're going to put the 5Z there. Next, and this is the most important thing. So, oh, I'm sorry, I didn't decrement the 5 counter. This is a 10. Okay, good. Now comes the most important thing, because we're seeing another B, another 1 here, 1B. Okay, let's go through it. J is 8. The contents is A of J, which is 1. Okay. The counter of 1 was at 3, but now it's at 2. Okay. And so we go to position 2, and what do? We place 1B there. Okay. Okay. And now we decrement the counter to 1. Okay, let's do it a little bit quickly. This 4 is going to go to 7. I'm going to decrement that and make that 6. This 2 is going to go to 4. And we're going to decrement that and go to 3. Notice we had that 3 already, so we're never really going to come to that again. Okay, the 6, we look at the 6. The 6 is in position 12. We put that there. The 5, Y, is going to go here. Oh, I'm sorry, I didn't decrement to 12. Okay, it doesn't matter because we're never going to see that one again. Okay, the 1A goes here. The 3 goes here. And the 5x goes here. Okay, that's sorted, but it's sorted properly. It's a stable sort. Okay, let me just tell you where you would have such a sort like this. Okay, imagine students in a college. Well, if it's a master's giving college, so you have freshmen, sophomores, juniors, seniors, first-year graduate students, second-year graduate students. That's 6 different possible students. So let's say you're a president of a college and you want to sort the students by these 6 different categories. Okay? But you have them now sorted in alphabetical order, and now you want to sort them by these 6 different categories. 1, 2, 3, 4, 5, 6. That's good, but you want them stable. In other words, you want them sorted in alphabetical order, in chronological order, 1, 2, 3, 4, 5, 6, but within each one, you want them in alphabetical order. So that's what this is all about. Okay, that's why you want it stable. Okay? Okay, so that's why you want this. Okay, so let's talk about the counting sort and how it works. Okay, how much time does it take? Well, this is K, this is N, this is K also, and this is N operations. So basically, it takes K plus N plus K plus N. We usually assume K is a small number, so basically this is 2N. 2N is a linear time sort. Okay, 2N is a linear time sort. So that's excellent. Okay, question. Okay, so first of all, it doesn't show up often, this counting sort. It's an interesting thing, but usually you don't have something like this. You wouldn't want to sort 20,000 names using the counting sort because you'd have to have 20,000 counting things. So that's not a very good thing. You'd have to have 20,000. That's not a very good thing. 20,000 different counters. You don't want to deal with that. That's a big pain in the neck. Okay, but they are specialty, and it's interesting. It's a violation of what we saw before. What did we say? Sorting takes n log n, and here we have something that works in linear time. What happened? What did we do wrong? And the answer is as follows. It's not sorting takes n log n. It's comparison sorting takes n log n. What do I mean by that? Every single sort that we saw, which makes a decision tree, what it does is it compares two elements, x and y. You take two elements in your thing and you're comparing them, and you're getting out two possible answers. Those things are called comparison sorts. Conclusion: there is no comparison sort that works with n log n, less than n log n. Comparison sorts need at least n log n. But notice how counting sort, I'm not comparing these guys to any other guys. I'm simply putting them in their right place. I'm not comparing, oh, this is more than this is less than this. I'm not comparing any two elements. So the comparison sorts don't work like that. This is a different type of sort. This is just a sort where you put things in its correct position. Okay? Not very useful, but interesting, and linear rather than n log n. So that's a very interesting thing. Okay. In a second, we're going to see another sort called a radix sort. Okay. So this is the radix sort, section 8.3. Let me show you the wrong way to do it, and then I'll show you the right way to do it. The wrong way to do it is as follows. I have a bunch of cards with 2 digits, and so I want to sort them in ascending order. So I put this 47 in the 40s column, the 28 in the 20s column, the 33 in the 30s column, the 22 in the 20s column, the 23 in the 20s column, 30, the 17 in the teens, the 18 in the teens, the 46 in the 40s, and you do this like this. Each card in there okay, now you have 4 different stacks because you have teens, 20s, 30s, and 40s, and now you sort each one. So 16, 18, and 17, you put that in ascending order. Okay, let's put this in ascending order. 25, 27, 26, 27, 23 goes first, 22 goes with that, 28 goes before 29. Put that in ascending. Okay, good. I sorted this. Now how do you sort this? 31, 32, 39 is at the end, 35 is there, 37 is there, 36 is before 37, 30 is all the way in the beginning, 33, find the right place for 33, 39, done. Now we sort this, 40, 45, 44, 46, 47, 40 goes there. Each one is in ascending order. You bring them together and you sort it. Okay, and now it's totally sorted. 20s, 30s, 30s, 40s, etc. So that's pretty good. Now let's see how much work we did. Okay, so you have, let me just make sure you can see this. Okay, not going to be the greatest. You have, let's say, n cards, and you split them up into groups of 4. Okay, and now you're going to sort each one of those. So how much does it do it? Well, I sorted them using a comparison sort, so it's basically n over 4 times log of n over 4. That's what a comparison sorts. Okay, you multiply this out, but you have to do it for 4 different things because I did it for 4 different piles. Okay, and so basically this is, the 4 cancels out with the 4 and you're left with n log n over 4. Okay, and that's about n log n. So that didn't save you much. Okay, it's a common thing to do. And this is a really divide and conquer actually. I split it up and did it. But I'd like to show you another way to do it, which is more what the radix sort is all about, and it's much more fascinating and much more efficient. So let's do my super, what is that called? Las Vegas sifting. Okay, and now I'm going to do something different. You ready? I'm going to sort it into different piles like before, but I'm going to do the least significant digits. So this is going to go in my 7s column. This is going to go in my 6 columns. This is going to go in my 3 columns. This is going to go in my 8 columns. This is going to go in my 2 columns. This is going to go in my 3 columns. This is going to go in my 9. This is going to go in my 5. This is going to go in my 4s. Okay. This is going to go in my 8s. This is going to go in my 9s. This is going to go in my 0s. This is going to go in my 1s. Ooh, bad spacing. This is going to go in my 1s. This is going to go in my 2s. This is going to go in my 6s. This is going to go in my 6s. This is going to go in my 7s. This is going to go in my 5, 5, 0, 7, 6, 7. Okay? Totally not sorted in any sense of the word, but now I'm going to do something interesting. I'm not going to sort each one of those. That would not help me a lot. Okay? I'm going to pick up the cards and put them like this. Just picking them up and putting them back onto the pile. Okay? Now what? Now, I'm going to sort them not by their least significant digit, but by their most significant digit. So this is going to go in my 2s column. This is going to go in my 3s column. This is going to go in my 2s column. This is going to go in my 1s column. This is going to go in my 3s column. This is going to go in my 1s column. The 47 is going to go in my 40s column. 20s column. This is the way I did it the first time. But now look, it's going to be much more interesting. 30, 40, 16, 20, whoops, 20s, 30s, 20s, 40s, 40s, 20s, 30s, 30s, 20s, 30s, 40s, 30s. Notice they're all sorted. They're all sorted. So I'm going to pick them up and put them together, and they're totally sorted. Question: how much work was done? Answer: I just went through the loop. I went through all n cards twice. That's it, just twice. 2n is a lot better than n log n. Okay, so that works amazing. The book has a nice example showing you how it works with 3-letter words and stuff like that. You'll have to do it like that, whatever. The point is here, also, we're not comparing the two cards. We're not comparing different cards. What we're doing is we're just putting them in the right places. And I did it with cards. The right way to do it is an array of linked lists. And you're placing things on your linked lists. And then you're gathering your linked lists together, and you're, again, spitting them out. Again, so the way to do this is with linked lists. Okay, so that's enough. So let's go through it. We're now finished chapter 8. Basically, sorting is n log n, if regular sorting. There are some examples of linear sorts, but they're not comparison sorts, and they're of limited utility, but they are still very interesting. Okay, so that's the end of chapter 8. Chapter 9 is something totally different. We'll see you next week. Take care.